A proton beam moves through a region of space where there is a uniform magnetic field of magnitude 2 Tesla directed along the positive z-axis as shown in the diagram. The protons have velocity of magnitude 3 times 10 to the 5 meters per second in the xz plane at an angle of 30 degrees to the positive z-axis. Find the force on a proton with charge where the charge is 1.6 times 10 to the minus 19. That's the standard electron charge. So here's our diagram. We've got the particle moving in this velocity v. It's 30 degrees here to the uniform magnetic field vector b. Here's our y-axis, here's our x-axis, and here's our z-axis. So just to go off the point a little bit here, but when here's we've got x, y, and z. Notice that when you turn x into y, you're getting z. So this is written down in the form of a right-handed set. So you know, if you're screwing if you turn x through to y, you see that it's like you're undoing a screw and it's coming out and it's the z. So that's defining a right-hand set. But that's like going off this question a little bit. So the solution is the right-hand rule shows that the direction of the force is along the negative y-axis. So we can see that because if we turn the velocity vector here into the magnetic field vector, so we're going to go like this, we're going to turn that v, so we're turning it, if you notice there, I'm turning it that way. So look, we're going into the page, so it's like a right-handed screw and we're screwing into the page. So the right-hand rule shows that the direction of the force is along the negative y-axis. So the force, we know the direction is going down here. So the magnitude is given by F equals QVB sine theta. So we got the angle 30. We've got the charge, the electron charge or the proton charge if you like. It's 1.6 times 10 to the minus 19. We got the velocity is 3 times 10 to the 5 meters per second, and we've been given that the magnetic field has a magnitude of 2 Teslas. Sine theta is 30 degrees, so it's sine 30. So we just plug all those numbers in, and we get a result of that the force is in this direction, and its magnitude is 4.8 times 10 to the minus 14 newtons. Now, here's the other way of doing it. So that was the geometric way, as explained in the problem solving strategies points 1 and 2 previously. Alternatively, we can do this in the vector language. So that's looking at, first of all, let's work out what the vector is for the velocity v. Now if we drop a line from there to there, we can see that because that's the angle 30, then this x component, obviously this x component here, parallel to, well, supposed to be parallel to that, we can see that that's, because that's the angle 30 degrees, yeah, and if that's right angle there, this distance here for the x component of this v is simply the hypotenuse times 30. So the magnitude of the velocity times sine 30 here, yeah, so it's v sine 30. So we've got 3 times 10 to the 5, sine 30, that's the I component here, so that's the I component. And for the k component, which is the z component, if you like, so along the z-axis, that's the k component. Obviously that's the cosine there, so that's so we're going along here now, so that's obviously the cosine, so it's cosine 30. So again, 3 times 10 to the 5 cosine 30, that gives us what this vector v is. And b, well, we know b is just 2 Teslas in the k direction, and so b here is just 2 units. There's nothing in any other. There's nothing in the I and the j. It's only in the k dimension. So that's 2 Teslas in this dimension. So that's b equals 2tk. And then for the force, then we're going to use that cross product here. So now the rules for the cross product, I think I've gone through this before. We write down the I. We just use the matrix determinant here. Finding the determinant of a matrix, really, we just write down the I, j and k, and then we ring this to find out the I component. We put a ring around there and a ring around there, so we're going 0 times 2. Obviously that the I component then becomes 0, and for the J component we put a ring around the J and a ring around this, so that's that times that, 2 times 150 times 10 to the 3 minus that times 0, so it's just J 2 times 150, so there we got that 150 times 2, K is 0, so we know that it's Q. We plug in Q here, multiply it out, and we get minus 4 points. So we get for the force vector minus 4.8 times 10 to the minus 14. So you can see here it's also given us the sign of that as well. So when working, so that's a really nice example. When working with a right-handed coordinate system and with that rule x, y and z there, whenever we find a vector and we do a cross product into that coordinate system for any set of vectors, we're going to get the correct sign here, yeah? So that's the beauty of doing this matrix determinant. So although we've done it geometrically, by just treating it all as vectors, we've got exactly the same answer, but the nice thing is it's given us the sign exactly of this force. So then we can just plot that out as minus 4.8. So here we can see it's minus J. Oh, sorry, I forgot to put the J down in there. So that's supposed to be J there, and it's down here somewhere. So that's a really nice example. If the beam consists of electrons rather than protons, the charge is negative, so we'd have Q equals minus 1.6, and the direction of the force is reversed, so the force, we'd end up with it going in this direction. The solution proceeds just as before, the force now directed along the positive y-axis. So that's a nice, very simple example, which just nicely covers the cross product quite well, I think.